In this video, we're going to cover the concept of bond polarity, which arises in covalent bonds in which atoms that have different electronegativities share electrons. So let's consider, for example, the bond that forms between two hydrogen atoms, between an atom of hydrogen and an atom of fluorine to form hydrogen fluoride, and the bond that forms between an atom of hydrogen and an atom of iodine to form hydrogen iodide. These are all covalent bonds. Now, if we look up the electronegativities of these elements, hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4.0. And iodine has an electronegativity of 2.5. And these values for electronegativity are going to give us some insight into how these two atoms in each of these bonds share electrons. So let's just calculate the difference in electronegativity. Electronegativity is often symbolized with the Greek letter chi. So the difference in electronegativity between the two atoms in the bond. Of course, the difference in electronegativity between hydrogen itself is 0. The difference in electronegativity between fluorine and hydrogen is going to be 4.0 minus 2.1, which is 1.9. And the difference in electronegativity between iodine and fluorine is 0.4. Now, in the case where the difference in electronegativity between two atoms in a bond is 0, what that would mean is that these two electrons are equally shared by both atoms. In this case, the difference in electronegativity is very large. And that means that fluorine is better at attracting the electron in this bond than is hydrogen. And what that means is that these two electrons spend more time around the fluorine than they do around the hydrogen. And that gives fluorine a partially negative charge, not a full negative charge, but the time that the electrons spend around the fluorine more often gives it a charge that's partially negative, symbolized by this Greek little d and then a negative sign. And then, of course, the hydrogen is going to need to balance that negative with a partial positive charge. The same thing occurs over here with a difference in electronegativity between iodine and hydrogen being 0.4, with iodine being the more electronegative element. However, in this case, the difference in electronegativity is not as stark, and so while these two electrons will spend a little more time around the iodine than they will around the hydrogen, the difference in electronegativity accounts for a smaller delta negative and a delta positive than what we see in fluorine. And I'm indicating that just by drawing the delta smaller in this case. Now, when there's a separation of charge like this, something called a dipole moment is generated. And a dipole moment is going to be something that we're going to designate by pointing an arrow from the negative charge toward the positive charge like this. And if we actually look at dipole moments are things that can be measured in molecules. If we measure the dipole moment in hydrogen, we find there's no dipole moment. 0 dBi. DBi is a capital D is how it's symbolized. That is the unit of measure for a dipole moment. The dipole moment measured in hydrogen fluoride is almost 2 dBi. And the dipole moment symbolized by the Greek letter mu for hydrogen iodine is 0.8 dBi. And so what we see is that when a bond is shared between two atoms that have a difference in electronegativity, that bond is going to have a dipole moment associated with it. And we clearly see that in the case of hydrogen, hydrogen fluoride, and hydrogen iodide. If there's no difference in electronegativity, there's no dipole moment in the bond, and in this case, no dipole moment in the molecule. And if there's a large difference in electronegativity, you're going to have a bond that has a very large dipole moment, and in this case, the molecule ends up having a very large dipole moment indeed.